afternoon. I'm continuing with my Milne to LCDM lambda cold dark matter mapping. If this works, I don't know for sure it will, but my plan is to convert the Milne coordinate system into lambda CDM by performing a couple of nonlinear transformations on this distribution of matter from what's essentially Euclidean space. In my last video, I had things kind of messed up. I've fixed this line, which I think I had number of Hubble observers in this section instead of events per Hubble observer, and so that caused some troubles. So basically this is just events per Hubble observer plus 1 to I times events per Hubble observer plus events per Hubble observer, and then I have I going from 0 to number of Hubble observers. But that fixed it so it runs without error, and I think I can adjust these on the fly. Let's see what it looks like with how many events per Hubble observer do I want? Say 20. And number of Hubble observers I want to make 20, sure. And what's the, this will make everything look a lot more compact. So that's what that comes out to look like. Now the next step is straightening these lines, these horizontal line, or the curves. I want to take that curvature into a straight line. And so my goal is to create, actually it's just to do a modification on group here. Group, because this is all my points in the demo. And what I want to do to the group, well, I have to think about this a little bit more, because I want to do something kind of like what I did to the LT list. I want to do this nonlinear transformation on every point in the distribution. And just for now, for lack of a better function name, I'm going to call this function name FoldOut, and it's going to take a I'll just call it a t underscore comma x underscore, and that is going to be a coordinate in time and then space. And I'm going to make a module. It's weird because I remember doing this just the other day, but I don't know where I did it. I created this function. And then the way the module works is basically I give a list of variables, then I give a bunch of semicolon separated commands ending with the output. So the module is going to have a list of variables called r and curly phi. And between those two variables, I'm going to say r is equal to square root of t squared minus x squared, and then semicolon, and then c phi equals arctang of t over x. And if that works right, no, not t over x. Yeah, t over x. Why is that not showing up in that form? Something to do with the division. All right, so, and then what it's going to output is r phi. It's going to be t is going to be phi? No, r. Oh, you know what? Let's just call this tau. Tau. Escape tau. Escape. We'll call that tau, and we'll put escape tau right here too. We won't call it R at all. We'll call it tau because that's going to be our ironic cosmological time. So tau equals that, and then we're just going to output R tau. No, tau times, sorry, escape tau, comma, and then we're going to put R times escape C phi. And I guess, yeah, I'm going to have to put another video in here to explain why this is tau times phi. Basically, it's an integral function, so I'm going to put that, I'll slip that in between the last video and this video. So that's our FoldOut function, but what I need to do is apply that FoldOut function to every set of coordinates in group. And it looks like this is almost exactly the syntax I need right here. Apply F. We're going to apply FoldOut to our group, which is a set of variables like that, and then we're just going to put in bracket or a curly bracket 1, and that should actually do it. So apply. We're going to have FoldOut to no, just comma, and what we're going to do that to is group, and then it looks like for some reason we've got this curly bracket 1, and I'm not sure why, but I'm just going to actually say group equals. So we'll abandon the old group and take the new one, because then we're going to be creating the Hubble world lines from that group and the ironiccosmoTime lines from that group, and then creating something with a whole lot of imaginary numbers in it. Okay, so what happened is I really need to just change this to x underscore comma t underscore, because that is the order that I put things in. And then down here, I need to make this t phi comma phi. T phi, tau phi comma tau. See whether that works. Great, now I have complex numbers. Not a good sign. Somehow phi is becoming is still turning into a complex number. And it was right here. This I did have as t over x. It should have been x over t. So once everything got reversed, guess what? We don't have the lines. We do seem to have straight horizontal coordinates, but I need to put the, and somehow we're getting 1 over 0 frequently. That's a problem. So the problem is that t is 0. This seems kind of awkward, but I'm going to try this. Instead of going from t equals 0 to this number, I'm going to have it go from, what is it, ePerHubObserver 1 over ePerHubObserver to 1 over ePerHubObserver. And then it will just get rid of all of the 0 points. Maybe. We'll see. And yeah, that looks like it worked pretty well. We're not getting that bottom where we get that. We don't have the origin represented, but we've got all of the other points, so that's good. Okay, so now that we've got that, I want to go back and put the Euclidean points into the original, and it would really be nice to make an animation from the previous, from the first to the second, but we really don't have any natural parameter here to use to convert, because see what's going on here? It's just t times phi, or tau phi comma tau. How do I go from x comma t to tau phi comma tau? Is there some kind of a transitional thing that I could do? I don't see any kind of transitional animation that I could do, not without some kind of creative technique. But then I'm going to go back to the Milne distribution minus the singularity point here. Notice that that point is gone. And I'm going to overlay a Euclidean, try to overlay a Euclidean coordinate system over the top of it, so that we can see what happens to Euclidean straight lines, the lines of actual simultaneity and Minkowski space for this particle, for that central observer, or the Euclidean observer. There's just one Euclidean observer in this distribution. It's this guy right here, who is stationary. All the rest of these guys are going to have planes of simultaneity that are tangential to this curve. So kind of what I'm imagining is creating a little box down here, and then 3 boxes, and then 4 boxes, and then 5 boxes, and maybe using the boxes to mark out the speed of light. I'm not sure if I want to get all the way over. Wait, let's see. If we went down to the bottom of it, we'll have 2. Let's do 2, then 4, and kind of imagine this being the 0, 0 point. Would it make sense to go in a straight line up that way? Say we'll define 3 points, then 5 points, then 7 points. And the question is whether we want the edges of it to be on x equals ct and x equals negative ct, or if that would cause some kind of errors when we apply the transformation. So in our generator function, first thing we want to do is decide how many points we want to have along this top row. So, so that would be, let's call it grid density. Grid density. And this is, let's call it Euclidean grid density for Euclidean grid density. So if I wanted Euclidean grid density to be 7, then this would be 0, no. Euclidean grid density, oh my gosh, this would be, wait. 0, 1, 2, 3. Let's say this is Euclidean grid density equals 3. Yeah, that would make sense. Then we go out 3 this way, and -1, -2, -3. So we're going out 3 both ways. And this would be 1/3, 2/3, 3/3 of the total third, third, and that would be the thirds of the total distance. So to kind of imagine what we'll be doing here, we'll have this point at 0, 0, which we actually won't use. And then we'll have this point at 1 over GD, 1 over grid density, comma, -1 over grid density, comma 1 over grid density. And this would be 0, comma 1 over grid density. And this would be 1 over grid density, comma 1 over grid density. Okay. The top level is going to be negative grid density over grid density, comma grid density. And that would be going by steps of adding 1 over the grid density each time. So we're going to have a nested loop basically for, let's call, I don't know, I equals 1, 2, 3, no, 1, 2, this is 1 over grid density, 2 over grid density, 3 over grid density, 4 over grid density, 5 over grid density, 6 over grid density, and then grid density. So 1 to grid density, step, or I plus plus, and then for j is going to be minus I to positive j plus plus. And then we'll have concatenating, well, we'll have to be adding something to the list. We'll be taking, we'll start with the list is empty, and then we'll just add to the list each time a point, which is j over grid density, comma I over grid density. And that will be how it's created, but then the trouble is we're going to also have to render it, which means we're going to have to access the individual points, which are going to go 1, 2, 3, 4, 5, 6, 7, 8. Wait, let me, we'll have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. This is going to be kind of weird because we're going to want to draw lines coming this way, 4 through 8, 9 through 15. And we're also going to want to draw vertical lines. Well, yeah, I think I'd kind of like to draw the vertical lines too, so we have some idea of where we expect the Euclidean distances to be measured. And you might be wondering, why am I working so hard to turn something that should be just a regular rectangular pattern into into this weird triangle shape? And it's because of this function right here, basically, and probably because of this function too. Both of those functions are going to give us imaginary or complex numbers unless we're in the correct quadrant. If we extend this over into the other quadrants, we're going to have errors and it's not going to render it properly. So we're getting towards the 20-minute mark. Not done with this project by any means, but I do need to say ta-ta for now because otherwise we'll run into sound issues.